All right, hello everyone. Thank you for attending today's Go with the Flow presentation. This is the second year we've hosted this expert webinar series, and we are very excited to share with the industry some of the groundbreaking variable path length applications being implemented across the world. The purpose of today's biologics industry about variable path length technology, commonly referred to as VPT, and how it could be implemented as an inline analytical measurement to provide real-time monitoring, drive better control, and minimize risk during the manufacturing process. Process analytics technology is a hot topic in the industry today. Strategic planning and coordination to properly implement concentration measurement as part of the PAT. We have brought together some of the industry's true pioneers in PAT implementation to share with us the process they took to implement the Flow VPX as part of their PAT strategy for various steps in the workflow. My name is James Gravinsky, and I'm the moderator for the event today. I'm the Analytics Sales Manager for the Mid-Atlantic US, and I'm really excited about where VPT is going and how our customers are applying it to their processes. Today, we have the pleasure of introducing Aishwarya Ramanan, Senior Research Associate from Seagen, which is formerly Seattle Genetics, based in Bothell, Washington. Aishwarya is part of the Seagen Purification Bio-Process Development Group and focuses her efforts on process analytical technology, strategy evaluation, and process intensification implementation for the downstream purification process. She received her master's in Bio-Pharmaceutical Engineering and Biotechnology from the University of Pennsylvania. Aishwarya has over 8 years of experience specializing in downstream process development and continues to drive innovation and optimization to the purification process. I want to give a quick reminder to everyone that throughout today's presentation, you can enter any questions that you have by using the control panel on the right side of your screen. There should be a tab for questions where you can simply type in your question, and at the end of the session, and we'll answer all of your questions. If by chance we don't get to any of your questions at the end of the webinar, we will be certain to address those questions with you in a timely manner. So I want to thank you everyone again for being here, and I will pass it over to Aishwarya shortly here to share with us the groundbreaking work she's been working on. The title of today's presentation is Implementing PAT Strategy Using the Flow VPX System for Inline Monitoring During Batch Continuous Chromatography. Aishwarya, thank you for joining us, and please take it away.
Thank you so much, James. Good morning, folks. I hope everyone is doing well today. And I appreciate all your time in logging on to this webinar and listening to what I have to say in terms of implementing PAT technology, in particular Flow VPX and downstream process development. Since James gave me such a beautiful introduction, I'm going to skip talking about myself and jump right into the content. So I will be starting by giving a quick introduction on the typical purification process flow and how and where PAT technology can come into play, followed by how VPX in particular helps with the process intensification efforts, be it in batch or continuous processing. And I'll be emphasizing more on real-time titer measurements, real-time binding capacity, especially with a dynamic load in between the process intermediates, and also talking a bit about the elution or the LUET collection criteria determination, followed by an overview on integrating the Flow VPX with the Repligen cross-flow KR2I system for automated TFF runs, and closing off with a summary and a takeaway from the overall presentation. So for starters, every industry already has a very well-established process with their batch chromatography. Why this craze to move towards continuous processing? And addressing the first point of smaller plant spaces, I think this is something we see even outside of the industry. As the demand is increasing, we are seeing smaller and smaller spaces available, and as such, that requires smaller setups. And with smaller setups, we are reducing waste, environmental impact, costs, and most importantly, the production time and the developmental timelines, because the scale-up requirement is reduced as you move on to a smaller setup. And this helps meet the improved or increasing market demands. And finally, this is going to enable automation, which could help reduce human errors and ideally improve the regulated compliance by automating the entire process. So just to give you an idea on what a typical downstream process flow would look like, is we have a production reactor from upstream, and the production reactor, the harvest is taken and processed over a depth filtration step or clarification step. And the clarified harvest is then, typically for MAPs, it goes through the affinity chromatography, and typically it's a protein A resin. And after the protein A purification is done, the eluate from the protein A pool is processed through a low pH viral inactivation step, and it goes through an additional depth filtration followed by a polishing step. And in some processes, it may be a 3-column step, and it may require a second polishing step. So after the polishing steps, it goes through a nanofiltration and a TFF or tangential filtration step, where you're concentrating your protein or your antibody to the desired concentration and dye filtering into the desired matrix. And finally, bulk filtration or sterile filtration and your final intermediate or bulk intermediate. The technologies we currently have that enables measurements, be it titer or in-process intermediates, protein concentration, or the final bulk concentration, are the CDEX BioHT analyzer. This is mostly used for titer measurements, as in harvest-related measurements, and this is a high throughput technology. And this is mostly offline, and typically, on an average, the results, the time taken to get the results are about 15 minutes, and sometimes it requires a dilution depending on how high or how low your standard is. And most industries started implementing the solo VPE system now as a replacement to the BioHT for titers and in-process intermediate measurements. So the solo VPE is also a offline measurement system, and it can be at line sometimes, and the results take about 2 minutes to pop out. And given its path length, it does not require any dilution for most part. And finally, we have the CTech Flow VPX system, which is an advanced and inline technology that can be compared to the solo VPE. And this gives us real-time results, and no dilution is required due to its path length. And it has a similar path length to the solo VPE, and it can measure very low to very high concentrations, again, similar to the solo VPE. So you all have an idea on what a typical excuse me, purification process flow would look like. And to give you an idea on where we can implement a PAT technology, so for starters, we can implement it for titer measurements or real-time titer measurements right after the harvest clarification and before the protein A. So this is going to help reduce the time taken to submit samples onto the BioHT and wait for results on the titer and start loading. So this can be immediate, and you can right away start loading your protein A right off of the harvest clarification. And the next step, you can implement it to establish your binding capacity of the resin, and this can be implemented on the protein A step all the way to your other polishing steps as well. During your low pH viral inactivation step, it can be applied to determine the appropriate titration based on your protein concentration. The depth filtration part, you can use the VPX to refine your depth filter collection criteria. For most part, we end up over diluting the depth filtrate, or there is tailing. That's in such cases, I think the flow VPX will come in very handy to determine a much narrower or accurate collection criteria. Can be used between the two polishing steps or at the end of the two polishing steps for eluate concentration measurements, and similar to the depth filtration, this can minimize the dilution with the flow through steps. Similarly, for nanofiltration, it can be used to determine the amount of dilution that is happening. And finally, it can be incorporated into the TFF system for inline concentration measurements. And this is going to be particularly handy if you're dealing with a product that has a density of over 1, then an inline concentration measurement is going to be more accurate. So this applying the flow VPX between the process steps is going to drastically reduce the hold times in production, and this could vary from industry to industry, but I think this is going to also allow an increased automation ability between the process steps. As a result, this is going to help efficiently convert the batch to continuous chromatography downstream. So starting with the harvest step, I think one of the major rate limiting step, excuse me, one of the major rate limiting step for a protein A or a capture step can be a low clarified harvest titer. And in this case, we have a technology out there that is called the inline concentrator, or an ILC, that can be applied to concentrate your harvest to your desired concentration. And what I'm going to talk about today is how this can help intensify your capture process and reduce your cycling time with your protein A or a capture step, and how the VPX played a role in this. So we have the harvest fluid, and then we have the inline concentrator, and then we have the protein A. And what was done is there was a flow VPX unit that was incorporated before the inline concentrator, as in the ILC load, and another flow VPX that was incorporated in the ILC permeate side. So to just give you a quick overview on how the ILC works is, it's an inline concentrator is a series of stacked membranes that helps concentrate your product that goes in, and by adjusting the retention time within or through the membranes, the stack of membranes, on a pressure basis, you can adjust your desired concentration factor that's coming out through your permeate line. So we have the VPX in the permeate line that is constantly measuring how much of a concentrated product you are receiving, and that can be loaded directly onto the protein A, or you can incorporate a surge vessel and then you can load it onto the protein A, and this is going to reduce your process volume in terms of the load and your processing time on the capture step. This can be implemented currently with batch technology, and this can be very efficient moving forward to continuous processing. So to give you an idea on how the data looks, so we incorporated the VPX and also used the standard CDEX BioHT to read different time point samples and to see how they correlate with each other. And as you can see from the graph, the VPX pretty much well aligns with the BioHT. And I think this gives a confidence that the VPX could ideally be an alternative to the BioHT in measuring concentrated harvest. And the advantage could be that this is inline and it can give you a real-time harvest concentration. So now that we have addressed harvest concentration measurements, how do we determine real-time titer measurements. And for this, the flow VPX from the ILC outlet or the ILC permeate remains online, and another flow VPX can be incorporated onto the protein A or your capture column effluent. So the difference between your column effluent and your harvest would ideally give you a titer. And you can see that the VPX pretty much well aligns with the BioSG. And the solo VPE values were taken as well because we have studies that show that the solo VPE can help with real-time titer determination. And I wanted to see how the VPX and the solo VPE compare to each other. And I think the percentage difference is very much acceptable based on this data. So this is going to help drastically minimize the titer wait times, especially in a manufacturing suite, and help maximize the resin utilization. If you're talking about real-time titer determination, you can also do a real-time loading capacity determination, as in you can maximize the use of your resin instead of sticking to a predefined loading density or loading criteria. And this can also be used as a secondary UV detector due to its wide path length ability. And this can come in handy if you're trying to move towards multi-column chromatography and you would like to use an existing system. So now that we have the harvest part checked and we have the titer determination part checked and how to establish a real-time loading or binding capacity onto resins at rest, now how do we measure, or how is it going to help with the LU-wet concentration? So for this, you place a VPX unit onto the column effluent, and the assumption is that at this step, you can use offline measurements as well, or you can keep the VPX in line with your previous intermediate, and you can use both the systems in place and get a difference between the effluent and the load, similar to what I was talking about with the harvest or the titer determination. And you can see you can get a real-time graph that can be plotted. And the graph very well aligns with how your typical UV chromatogram would look like. And almost all industries out there that is doing downstream processing use an ACTA. And they base their collection criteria off of the ACTA UV readings. And they typically determine a UV cutoff for the start and stop collection criteria. And the one disadvantage that could happen at times is that you may end up over diluting your pool, or which could lead to a longer loading step with your with the next step in process. So what the VPX can help is do a real-time cutoff based on concentration instead of relying solely on the UV cutoff off of the ACTA. And this is going to help minimize dilution that you may see in situations where you see tailing, or in situations where you end up over diluting your product for various reasons. This is going to help enable continuous processing because this can ideally eliminate your hold tanks or intermediate tanks. And this is going to come in very handy when you have smaller space requirements. So just to give you another overview or a quick recap on what the downstream process steps involve, and what if we were to move towards continuous upstream? Say continuous upstream in today's words means perfusion. So assuming a 14-day perfusion process, this is going to be a bottleneck for downstream processing, because you're talking about perfusion that's constantly perfusing your product of interest, and your downstream will have to be equipped enough to handle the increased expression out of the cell culture process. And that's where your first step of the process takes the most hit, and you're looking at probably up to 14 cycles of depth filtration. And if your titers are lower, then you're talking about maybe 4 cycles of your capture step per day, and ideally up to 14 cycles of the rest of your process steps as well. So to tackle this, or to tackle the increased expression out of the upstream process, the first step, if you're trying to stick to batch or semi-continuous mode, is to intensify your batch process to load until you see a certain percentage breakthrough, instead of using a predefined loading density. And basically, you're also helping utilize or maximize the utilization of your resin. And given today's situation with the supply chain, especially after the pandemic, and also factoring in the inflation rates, I think most industries are looking forward to maximizing the utilization of their current resins. And this could be one of the spots to start. This can enable continuous processing, as in you can apply it for inline concentration measurements, and ideally moving towards multi-column chromatography. And if you are moving towards multi-column chromatography, you can apply the flow VPX inline, and you can do a real-time optimization during the loads or during the entire chromatography step, in terms of the loading, the washes, the elution, the regeneration, etc. So this is again going to minimize the workload for analytics, and also reduce the wait times on our end for the results from the various groups. And a quick idea on how this can be done is quickly with batch process intensification, load until you see a certain breakthrough. The VPX can be applied on the column effluent side, and applying the very first principle of including a flow VPX onto the column load or the harvest side. With multi-column chromatography, I kept it open-ended, saying UV cell outlet, because this can be incorporated between 2 columns, or it can be incorporated into the appropriate flow cell outlet, depending on how many columns in series are using that outlet and where exactly you would like to place your VPX, and what exactly are you looking forward to in terms of the information coming out of the VPX or optimizing your run. Just a quick idea on how the data could look like. So for starters, you're loading onto your first column in step, and you have this is your effluent, which is ideally a baseline, until you start seeing a breakthrough of your product of interest in the effluent. And once you see the breakthrough, you can skip towards your wash step, and you can optimize or hold your wash until you see all your protein or all the impurities getting washed off of your column prior to moving on to the next step in your process. This data was generated using a multi-column chromatography mode of operation, and this enables real-time process optimization. So talking about real-time concentration measurements, the one spot that I think Repligen has made it very easy is incorporating the cross-flow KR2I system along with the VPX. And I think pretty much most industries are aware that aware of the cross-flow TFF system, and now that the Repligen has brought out the VPX integration with the cross-flow system, you have a better accuracy for your stop criteria with your TFF system, because it can be made concentration based as opposed to just mass based. And this is going to be very helpful if you're dealing with products that have a density greater than 1. And this helps avoid gravimetric dilutions and wait for offline measurements, and then having to do a reconcentration or redilution. And it's going to help automate this step and better accuracy of your process. So this is what the plot could look like, and I think just looking at the VPX data and your concentration factor, you can see that they align very well, and the concentration factor versus the concentration, I think they're very accurate, and you can see that you can monitor your product concentration through the dye filtration step as well, that it remains stable, and this can help with real-time managing your process with the TFF step as well. If you needed to concentrate it more or concentrate it less or move to the next step, I think this will come in very handy for purposes like that. So final takeaway or an overall summary is that FlowVPX as an inline PAT technology can be applied to our current batch processes, and it supports process intensification efforts, especially with real-time measurements or real-time dynamic binding capacity estimations. And it can also be used as an inline column UV detector or an add-on inline column UV detector to measure breakthrough, to optimize washes, or to measure or redefine your eluate collection criteria. And as a whole, this is going to help ease automation and enable us in taking another step towards continuous processing. Thank you so much.
Thank you so much, Aishwarya, for the wonderful presentation. Wow, that was really great. I hope everyone on the call got a very good introduction into a lot of your processes. We're going to jump into a Q&A session here. I want to remind everybody on the webinar that the box on the right there can be used to input any questions that you may have. I'll kind of give to here just for people to enter any questions they may have as well. I want to give a special thanks here to Aishwarya for sharing this great work being done. And we look forward to all the great things that are coming from you here in the future as well. So let me kind of get into some questions that are coming in here. If someone is new to FlowVPX, where do you think the best process step is to start? Where would you get the most bang for your buck? I know we saw you go all the way from your basically your batch reactor through columns all the way to your concentrating up step in UFDF. What steps in the process do you think are kind of good for you?
So I think for a beginner, I think the appropriate step or the ideal step to start with could be the TFF step, because with the cross-flow KR2I system, I think we have the VPX that can be easily integrated into the system. And this can be one of the challenging steps, especially like I mentioned, if you're dealing with a product that has a higher density than 1, then I think having a more accurate TFF step would be very handy. And also one of the easier steps to implement the VPX can be with the process intermediates, the eluate collection criteria measurements as well.
Okay, awesome. Thank you so much. Next question that's come in here. What is the minimum flow requirements? Can the flow be returned to the process, or is it sent to waste?
So it depends on where in the flow that you place the VPX. For instance, the VPX unit can be placed to your fraction collector if you're talking about collecting fractions using an ACTA. In that case, all you're doing is directing your product through the VPX to your fraction collector instead of directing it to the waste. So I think it can be modified based on your requirement. And it's going to depend on what instrument you're using to imply.
Yeah. Sounds good. Yeah, I'll quickly elaborate a little bit more on. So the flow VPX itself, the instrument is non-destructive, right? So you can return this into your process stream. You can continually cycle it through, or if you're looking to monitor for things that are waste, you can flush that to waste exactly. And then minimum flow requirement, there's no real minimum flow requirement, just as long as things are flowing to prevent any protein from kind of building up the system itself. So thanks, Aishwarya. Next question we have here, is the software interface user-friendly? Does it integrate into other automation platforms such as Delta V, or can it send, for example, a 4 to 20 milliamp signal?
Yes, so the software is fairly easy to toggle around with and very straightforward. And it can, I'm not entirely sure about the Delta UV connection, but it does have the 4 to 20 milliamp setting or IO that can be used along with other instruments that support the conversion.
And yeah, I can answer that portion of the question on Delta V. Yes, we have an OPC UA. You can integrate directly into Delta V as well. Next question here that I see, what are some of the challenges you foresee with implementing an inline device like FlowVPX in continuous manufacturing, and how would you look to overcome those?
So currently this is still in the process development analysis stage. So I think the first step would be to scale up implementing the VPX. And I think even within the process development stage, you're going to have to look at comparable data, for instance, with Solo VPE or other standards that the industries may be using in particular. And I think scaling it up can be the first challenge to overcome. And I think from there on, I think we'll have to think about implementing it in manufacturing and further down lane, the continuous manufacturing.
Awesome. Thank you so much. Another question. One slide mentions inline measurements using FlowVPX can reduce hold times in production, allow for increased process automation. Do you see the FlowVPX being used as an IPC or real-time release, or for real-time release in the future?
So in terms of the production wait times or the result wait times, I think this can vary from industry to industry. So I'm not going to give particular numbers, but I think when you're talking about, say, a solo VP to a full VPX comparison as well, you're talking about an offline measurement that could take anywhere between 2 and maybe 10 minutes in terms of taking the sample, walking there, reading the measurements, and then getting the data off of the solo VPE. And compared to that, a Flow VPX, which can give you real-time data, I think that is going to be a time saving. Yes, the VPX can be incorporated with the in an IPC setting in the future. Yes.
Okay.
I hope I answered the second part of the question, right?
Great. Yes, I hope so. If whoever wrote it has a further question, they can feel free to type their follow-up question into the box. Your continuous manufacturing slide is the ideal state. How realistic is that? AKA, how long would it take to implement this technology and transfer it to manufacturing? Do you see any potential pushback from regulatory bodies and authorities?
So at the moment, I cannot speak to implementing this outside of PD for proprietary reasons, but I think for any new technology out there, I think you would need extensive data to support the technology. You're going to need extensive validation to support the technology as well. So I think as long as an industry has all that sorted out, I think it should be straightforward to implement it.
Okay, great. Yes, I think so there are various people that are starting to transition their instrument into manufacturing. And just to let the person that asked the question know, we can certainly assist. We work with folks, as I'm sure you've experienced, Aishwarya, yourself, to help with any processes as they continue to kind of move through their implementation of their units into various streams and everything. So we're always willing to help out with everybody with that. One more question I think that just came in here. If you were trying to measure CF across an ILC, would you need two VPX systems, or would you just alternate between the feed and the permeate using a single system?
So it would be nice to have two VPX systems because you're doing an apples to apple measurement as opposed to using a different system. And having said that, you can also use a flow VPX on the permeate side of the ILC and use the solo VPE on the feed side of the ILC if you're assuming your feed is not changing drastically, or just try to take several measurements at I don't know, various time points or such. But I think toggling between your feed and your permeate side with a single unit can be challenging because the ILC is more of a continuous flow, and disrupting the flow, I think it's going to be a struggle.
Sure. Yeah, that makes sense. That makes sense. Thank you so much. I want to give it just a quick minute here. I think that's all the questions that we have currently received. So I just want to give it a quick minute to see if anybody else has any questions that they want to toss your way as well. Again, Aishwarya, thank you so much for taking the time to present to everybody this morning. This was a wonderful presentation, and we look forward to many more things that come out of Seagen's laboratories and everything as well. So I think if there's no other questions that I see come through, people can feel free to still ask us questions. We'll be sure to answer them for you offline. But for now, I think we will end this discussion here. And I do want to remind everybody on the call that next Thursday, I believe, we will have Go with the Flow expert panel discussion that will be live at the same time, 8 a.m. Pacific, 11 a.m. Eastern, and 5 p.m. Central Summertime. Oh, I apologize. I just got notified that it's this Thursday coming up. So in a couple of days here is our expert panel discussion. So without, I think I just had one last question come in. Sorry, Aishwarya. Here we go. So does the VPX use fibrets like solo VPE? I'll let you take a crack at it unless you want me to answer that one directly.
I'm pretty sure you'll give up more details on this front, but no, the Flow VPX does not use the fibrets like the solo VPE, but it has the I think I'll let you take.
Sure. Yes.
Yes.
Absolutely. You're almost there. Yes. To answer the question, the solo VPE, as you know, uses the disposable fibrets. What's in the Flow VPX is actually a stainless steel fibret. So then basically what you're doing when you flush through and clean, what you're doing is essentially also cleaning that fibret tip from the Flow VPX. So yes, it has a stainless steel fibrate that is significantly more durable than the exchangeable fibrettes that are on the Solo VP. And just to let that person know as well, we go down to 1 micron. We go all the way down to 1 micron measurements using our fibrettes as well. So I think that sounds like all the questions. Again, I want to thank everyone here on the call for their time and participation in this wonderful, wonderful series. And Aishwarya, again, thank you so much for your presentation. It was absolutely wonderful. And we will look forward to everybody potentially attending the Go with the Flow expert panel discussion that Aishwarya will be on in a couple of days as well on Thursday. So if no one else has any questions, I will end this webinar again saying thank you so much, and we will see you guys soon.
Thank you so much.